This is a demo of the test prioritization tree creating process via a decision tree method on a Markov decision process. This tree gives a contingency plan for which test to take given the values of other tests. We can see that before any other tests have been performed, the most informative test is the ToxDragon B020S. Given the top value for this test, the best second test is ToxDragon J. Given the bottom value, the best second test is ToxDragon JG17. These trees are built using QSAR and in vitro chemical data. Tests starting with the ToxDragon and QSAR tests. As you can see, almost all the informative tests are ToxDragon tests, with 4,900 matches. (4,946). One notable exception to the ToxDragon tests you see here is the ToxATG tests, which you get to by a top value for ToxDragon B and the bottom value for ToxDragon J. To create this tree, we started with an endpoint that we were trying to build a test prioritization framework for. In this case, we have chosen cholinesterase inhibition. We then use our data set, which is quantitative structure-activity relationship data and in vitro data, to create a classifier that can return probabilistic classifications. This classifier tells us both whether a chemical is positive for this endpoint or not positive, and it also gives us the probability of that classification. We then build a table of joint probabilities for each possible test. This table tells us the probability of one test value given all the other test values, and it should be able to give us this value for missing values as well. So when we're starting here, our joint probability table tells us the probability of getting an up value for ToxDragon B02 or a down value for ToxDragon B02. Once we have the joint probability table along with a probabilistic endpoint determination, we can build a greedy test for prioritization by choosing the test that reduces Shannon entropy on the endpoint prediction by the most at any point in time. We can improve on this process by doing a reinforcement learning technique for choosing tests. For example, it's possible that some tests may predict for other test values very accurately while failing to predict for the endpoint very well. We might call this a transitory test, as it gives us the ability to predict for transitions between testing states. The current greedy framework for the test prioritization will fail to detect any transitory tests. And now I'll just show you a little bit of the expansion of this tree, and you can get an idea for how large it is. Some of the important next steps in this graphical user interface will be to show what the actual values are for each of the branches on this tree, as well as to show colors for each cell telling us how likely it is for a chemical given these test values to be toxic. This is actually an abbreviated tree, and a completely finished one will go much deeper. But you can already see that the branching values are significant. Here you can see at the end of a tree here we have an 89% probability for toxicity, and in fact pretty much all of these values are 89%. So we can expect that without having to do too many tests, we're going to get consistent values for probability of toxicity.